Okay. I'm just waiting a couple of seconds until the recording starts, and then we can start the presentation. Okay, recording started. We can start as well. Okay, Mama, if you can't see it now, you will see it by the end of today, inshallah. Okay, we're having some issues with Moodle. Well, I am having some issues with Moodle, but inshallah by the end of today it will work out. Okay, share screen. We shall continue. Unfortunately, that is not possible, Shima, because I already have another lecture at that time. Okay, but I am receiving many questions by email. I will try to reply to them as soon as possible. Okay. Oh. What do you mean ما حد يجاوب على أسئلتنا؟ Okay, can you do me a favor, Shema? Can you email me or stay on after the end of this lecture and we can discuss this further, okay? Because the instructions are for questions to be answered in the tutorial section. Okay, let's speak about this after this lecture. Once the lecture is over, please stay back, don't leave, and we can discuss this further. I need to know more about this to address it, okay? Because the instructions for tutorials have been very clear. They are there to answer questions. If we're not answering questions, then what are we doing? Okay, so towards the end of the previous lecture, okay, we discussed projectile motion and uniform circular motion. And we said we're going to be talking about relative motions. And so I'm going to start today by showing a few slides and then talking a bit more. Okay. Check this out. You're in outer space, you're in vacuum, so you don't have to worry about things like, you know, air resistance or anything like that. Now, if I'm on the outside and I'm looking at a space shuttle and a satellite, they're both moving, here is what I see. Let me just open the chat window so that I can see if you're writing anything while I am. Okay, so if I am on the outside, here's what I see. Okay, one of them is going faster than the other. I'll repeat it. The satellite is going faster than the space shuttle. This is what I'm seeing when I'm on the outside. What happens, though, if I am on the inside of the shuttle? Here's what I see. It looks as if I am not moving, and the satellite is the one that is moving at a certain speed. Okay, now if you look carefully at the speed the satellite moves here, it's moving quite quickly. But here, it appears to move slightly slower. Now, you might know already what I'm talking about. Sometimes you're sitting in the car at the red traffic signal. You're looking out the window, Sarhanin, and then suddenly you're not really sure, is my car going in reverse or is the other car going forward and I am standing still? Now, what happens if they're both moving at the exact same velocity, in the same direction, same speed? What will I see on the inside? If I'm inside one of them, if I'm inside the space shuttle, what will I see? No one? Well, here's what I'm going to be seeing. This. No, your screen is not stuck. If we're both moving with the exact same velocity, then it is going to appear to me, okay, as if the satellite is just stationary. It's not moving. Okay, what about this? Now I have accelerated, and my velocity in the space shuttle is much, much quicker than the satellite. So when I am on the inside, what am I going to be seeing? I'm going to see as if the satellite is going in reverse. The satellite is not actually going in reverse. The satellite is still going. The satellite is still going forward, but at a velocity that is slower than mine. So it's going to appear to me as if it is going backwards. Okay. What are these called? These phenomena that we're used to, that we see on a daily basis sometimes, what do we call them? We call them relative motion, but we'll come back to this terminology in a second. We need to define something first. Yes, exactly, I have. Measures of position and of velocity depend on the reference frame of the measurer. What does that mean? It means that it depends how me, the person who is observing the motion, how fast am I moving? How am I moving? In which direction am I moving? Okay. Now, usually what we do is we see our usual reference frame is that of the ground. Yes, Earth moves and Earth rotates, but when I'm sitting right now, I don't feel that rotation. It feels to me as if Earth is just stuck. So what we do usually is we measure our velocities with reference to the Earth, as if the ground is stuck. So when I'm saying my velocity is 120 kilometers per hour north in a car, what I am actually saying is, compared to the ground, which I am taking to be not moving, I am moving 120 kilometers per hour faster than that not moving ground. Okay. So what we do is, for each object of motion, we define a set of coordinate axes. X1, Y1, Z1, X2, Y2, Z2. What do we do with these? Well, what we do is, say we have two cars, for example, moving. Okay. Each one of them will have a different velocity, VA, VB. Normally, this happens on a road. But the question is, if I am inside one of the cars, how do I see the velocity of the other car? Okay, so if the cars are both moving at 10 meters per second, I can say velocity AG is equal to 10 meters per second. Velocity BG is also equal to 10 meters per second. So with reference to ground, A is moving at 10 meters per second, B is moving at 10 meters per second. So to be clear, we will be defining this AG to mean velocity of A with reference to G. Okay. Now the question is, what is VBA? What is the velocity of B with reference to A? If they are both at the same velocity, it will simply be 0. It will appear as if we're both not moving. Yeah? Perfect. AB, velocity of A with respect to B, is again the exact same thing, 0, because we're both at the same velocity. So far, so good. No complications. Now the question is, what happens if the red car is moving twice as fast as the yellow car? Now things become a little bit more complicated. Things have changed. Ryan, yes, in the first example, it was 10 minus 10 equals 0. But now we have one going at 10 and another one going at 20. So things are slightly different. So VBA, so when I am inside B, and if I take A to be my reference frame, it's going to be 10. Because I'm moving at 20, yeah, red is moving at 20, yellow is moving at 10. So when you're inside the red car, it appears to us as if yellow is only moving at, as if red is only moving at 10. What about the other way around? What is VAB? What is my velocity of A if I take B to be my reference? Excellent. Minus 10. Because for each second, it will appear, because that car is going faster than me, for each second, it's going to appear as if I am actually going backwards 10 meters. Excellent. Let's see if we can do this with a few numbers. Cars A and B are moving away from each other. Car A moves north at 25 meters per second with respect to the ground. Car B moves south at 15 meters per second with respect to the ground. So I'm going to draw it. Car A is going north at 25 meters per second. Car B is going south at 15 meters per second. What is the velocity of A with respect to B? So I want V, A, B. Forty north, ثلاثة, 3, C. Okay, so pretty much every single person got it right. Okay. The correct answer is this. We have car A going at 25 meters per second minus car B, which is going at 15 meters per second, but in the other direction, which ends up with 25 plus 15, which is 40 meters per second north. I'm really happy that pretty much everyone got this correctly. Okay. Let's present this in a more formal mechanism. My yellow car and my red car, whatever happens with respect to the yellow car, I'll call in frame A. Whatever happens with respect to the red car, I'll call frame B. How do I relate these two motions? So, the reference frames at any given point, if these two velocities are constant, I am not looking at accelerating cars at the moment or accelerating frames of reference. This is slightly more complicated, and I'm not going to be doing that right now. So, if I have a yellow car moving at some velocity, VB, and a red car moving at some velocity, VA, and a police car, one that is moving at V police. Okay, so I'm going to write VA, VB, V police. Then the distance between B and A is given by XBA, and the distance between the police car and the red car is given by XPB. Too many letters, we'll explain in a second. Now, I want to know what is the distance between the police car and the yellow car, XPA. How do I do this? Well, just from looking at the photo, I simply take this distance plus this distance. Rather simple. So far, no problems. Okay, at least without numbers, the idea looks really simple. The positions in different frames, okay, are given by, I take the position of one object plus the position of another object, it gives me the position of the third object. Very simple. The distance between here and here is equal to this distance plus this distance. Very simple, right? No complications. What about velocities? Well, let's take the derivative. If I take the time derivative of each component of that very simple equation, it will give me the velocity of one is equal to the sum of the velocities of the others. Again, very simple. This is what we did in the example before, yeah, with the north and south cars. Very simple. But then what happens for accelerations? Okay. Accelerations will be related with a different equation. Why? For purposes of this course so far, why is it stuck? Okay, give me a second. My computer is not responding. Okay, my computer decided to be okay again. Let's do this on a whiteboard. We have object A moving in this direction, we have object B moving in this direction, and we have object C also moving in this direction. Do we agree that the distance between A and C equals the distance AB plus distance BC? Few yeses, one no. Okay, pretty much everyone says yes. Okay, so we agree that the distances add in this way. No worries. Velocity equals the first derivative of distance. So we get VAC equals VAB plus VBC. Do we agree on this? فوق الX نقطة معناته derivative. So this is the same as writing this, just in a different way. Okay, so we agree on these so far, right? Okay. Now, let's try to extend this to acceleration. Acceleration is equal to d by dt of v, which will give us acceleration of AC equals acceleration of AB plus acceleration of BC. So far, so good? Do we agree on this? Few no's. Okay, could someone who is saying no explain to me why no, and someone who is saying yes explain to me why yes? No? No explanations? Okay. Mathematically, everything we have done so far is consistent. We have agreed this is for A, this is for position. We have agreed this is for velocity. And if we simply take differentiation, then this equation is absolutely correct. Now, we bring in our rule. Okay, this equation is absolutely correct. There is no problem with it. The only thing is, we are going to be studying a simple subset of the general rule. We're not going to be studying the general rule. We are going to say that A and B are going to be moving the reference frames. So we said this one will have XY, and this one will have XY, right? We will say that the acceleration between these two is equal to 0. We are only going to study the case where the two bodies of observers, the two observers, are not accelerating. Why? Because if we accelerate, it becomes more complicated and we need to do some more complicated physics. Okay, so we are going to be looking at a simple subset of problems. Okay, now, if I say my observers are not allowed to accelerate for this course or for this problem, okay, so if I'm looking at something, I cannot look at it while I'm accelerating. I can accelerate, no problem, but I'm not allowed to look while I'm accelerating. While I'm accelerating, I'm going to close my eyes. Then my acceleration of AB is going to be equal to 0. And this will give me a slightly different equation. It's going to give me AC is equal to A BC. Okay. What does this tell us? This tells us if I have two observers who are looking at something from far away, both of them are moving at a constant velocity without acceleration, whether observer A is looking at C or whether observer B is looking at C, they are going to see the same acceleration. Okay, it doesn't matter if, say, for example, C is moving this way. I have A here and B here. Say A is moving at 10 meters per second, and B is moving at 10 to the 4 meters per second. Okay. If this acceleration is 1 meters per second, these two are going to see it exactly 1 meters per second. Okay, so we can use the exact same equations without problems. Let's do an example with numbers. Okay, it might make it slightly easier. We have three cars, yellow, red, and police car. VBA is 52 kilometers per hour. So if I am inside A and I'm looking at B, I will see B moving at 52 kilometers per hour. VPA, if I am inside A and I am looking at the police car, I will see it coming at me at 78 kilometers per hour. What is VPB? So if I am sitting inside A, I will see the police car come at me at minus 72 kilometers per hour. If I am sitting here, how fast will I see the police car coming at me? Okay, well, we use our nice rule, VPA equals VBA plus VPB. Okay, we have two answers. One says minus 130, one says 26. Let's take a look. VPA equals VBA plus VPB. So I'll give you options to make it easier. Okay. Here are your options. Police car P is moving east at 130, west at 130, east 78, west 78, east 52, west 52. The correct answer is, as most of you said, 130 kilometers per hour west. Why? Well, I know that if I am in A, the police car is coming at me at minus 78. I know that the red car is already going at 52 kilometers per hour, which means if I am sitting inside here, what I will get is minus 78 minus 52, because I'm going 52 in the opposite direction, which gives me minus 130 kilometers per hour. Since I have a minus here, it means that it's coming in this direction. This direction is west, according to the very famous rule, never eat silly worms. Now, if police car P brakes and stops relative to car A, because this is a velocity calculation. Remember that this is not just a speed calculation. Yeah, we have left speed calculations way back. Okay. Now what we are doing is everything we're doing is velocity calculations. So the directions are very, very important. 52 is different to minus 52. 52 means it's going in this direction. Minus 52 means it's coming in this direction. If I have two cars going at plus 52, then their relative velocity is 0. But if I have one car coming 52 this way and one car coming this way, then my relative velocity is 104, which is double. Okay. Now, if police car P brakes and stops relative to car A in time 10 seconds, what is the acceleration of P relative to A, APA? 5.2, 2.2, 7.8, or 0? 7.8. Someone else said 7.8. Let's do it. If P brakes and stops relative to A in time 10 seconds, what happens? Well, V equals U plus AT, correct? What is A of PA? What is A of PB? What we do know is A of PA is equal to A of PB. This is supposed to be 4.38. Okay. So let's do it. Final velocity is equal to 0. Initial velocity was minus 50 something. I don't remember. Minus 78. Plus A in 10 seconds, which means it is 7.8 meters per second squared. And there's a minus because it is decelerating.
But doctor, while shifting to get the value, the minus sign would be cancelled.
You are absolutely correct. The minus sign will be cancelled. What is the acceleration of P relative to A? We are also coming in the opposite direction, so you are correct. It should be like this. 7.8 meters per second squared. Okay. Why? Some of you might ask, but we're slowing down. Why don't we have a minus sign? Remember, our velocity was minus 78. So you are going towards 0, and you started at -78. So your acceleration is 7.8 meters per second, and it's taking you per second square, and it's taking you towards 0. Okay? If my velocity was 78, then my acceleration would be -7.8 to take me to 0.
Doctor, why velocity here equals 0?
Sorry, say that again.
Why the velocity equals 0 in this equation?
Because p breaks and stops. So stops means velocity becomes 0.
Okay, thank you, Doctor.
Sure. Okay. Let's take another one. A train is traveling east at 26.8 meters per second relative to the ground. A passenger is walking to the front of the train at 1.7 meters per second relative to the train. So if this is my ground at 0, my train is going this direction at 26.8 meters per second. And a person is going 1.7 meters per second relative to train. And this is important, not relative to ground. Directly overhead the train is a plane flying west horizontally at 257 meters relative to the ground. So I have a plane here, and it's going 257 meters per second west. What is the horizontal component of the velocity of the airplane with respect to the passenger on the train? So we want velocity of plane with respect to person. Someone said B. B, A, D. So some are saying this, some are saying this, and some are saying this. No, not A, D. Okay, I have one person who's saying this. Okay, so we have agreed إنه هذا من المغضوب عليهم. No one wants this one. Let's do the calculation. V of P person is equal to V of P ground plus V of train ground plus V of person ground. Actually, no. What is the horizontal component of the velocity of the airplane with respect to the passenger on the train? Sorry, my bad. On VP passenger. So we want V of why is it not writing? Okay, not writing. Let's do it by calculation. We want a V of P with respect to the person. We know the person is going 1.7 meters per second that way with reference to the train, which means to the ground, V, oh, it's working again. V person ground is equal to 26.8 plus 1.7, 28.5 in the east direction. Okay. Which means that if I want my velocity of my plane with respect to the person, V plane person will be equal to V plane ground plus V person ground V P ground plus V person ground no, we'll need ground person. So we get V plane ground 257 west plus V ground person, so it's minus 28.5, sorry, plus 28.5, which is 285.5 west. Why don't we subtract on the last step? We can subtract, but then we will end up with minus minus because the person is going in the other direction. Okay, so what we're thinking of, this is the one way to think of it. This is how I think of it. Imagine my person is 0. So if I know my person is going at 28.5, okay, let's imagine the person is stuck, 0, okay. We know that our person is going at 28.5. So if I want to make everything relative to this person, okay, I need to think of it as 0. How do I make everything 0? If I am standing still and this person is moving at 28.5 in that direction, it's the same as that person standing still and me going 28.5 in this direction. Yes? Let's switch to a whiteboard. Let's switch to a whiteboard. Hopefully that would be easier. برسم مرة ثانية وبرسمها على الوايت بورد بدون الكلام. اوكي. الحين عندنا شخصين. If I say this person is not moving and this person is moving at 10 in this direction, this is the same as me saying, from a physics point of view, this person is not moving and this person is moving at 10 in the opposite direction. Do we agree so far? Yes? People who were saying اختبست? Question marks. Okay. So far we're okay? We agree on this, right? Okay. So If we take the ground to be 0, we know the plane is going 257 in this direction, and the person is going 28.5 in this direction. So far, so good. Now I want to make the person 0 because I want the velocity of the plane relative to the person. So the person is now going to be 0. He's not going to be moving. So the only way, so what I do is 257 minus 28.5 is equal to 285.5. Okay, I need to add that velocity somewhere. Since I made that person 0, I added to the velocity of the plane. So بالناتج, each 1 second, whether we look at 1 or 2, okay, the distance between the plane and the person at any given time in 1 second will increase by 285.5 meters. Either we say this goes 257 and this goes 28.5, so the distance is still 285.5, or we say this guy is stuck, this thing is going to 85.5, the distance is still 285.5. Is this better?
Doctor, I think the velocity of plane relative to ground should be in minus because it goes to west.
No problem. Then the other one make it positive.
Yeah.
No issue at all. So if you want, if we are another way to say it is, you said you want it this way.
Yes.
This is also correct. In that case, what you say is minus 257 plus minus 28.5, because it's in the opposite direction. You get minus 285.5, which is the same. So whether I say 285.5 west, or I say minus 285.5 east, or I say 285.5 in the minus east, it's the exact same thing. Okay.
دكتور
ايوه.
بس ليش خلينا بالاثنين سالب؟ ليش ما خلينا واحد سالب باعتماد انه واحد موجب يكون الثاني عكسه، ولا كيف؟
وين هنا؟
ايوه، يعني مثلا احنا بناخذ 28.5 بالموجب والثاني يكون عكس الدايركشن يكون سالب، ليش خلينا اثنين سالب؟
So like this, minus 257 plus 28.5.
ايوه.
This is correct if this is with reference to ground. with reference to ground, this is correct here. Look, 257 in this direction, 28.5 in this direction. Okay. All right. Let's move on. All right. So moving on, so far we have spoken about what is physics about. We have spoken about vectors, which is mathematics, and then we did chapters 3 and 4, which is on equations of motion, which helped us explain how do they move, okay, but not why do they move. So now we're going to start looking at the why to explain the how that we already did. So we already know that V equals U plus AT, S equals UT plus half AT squared. We know these equations. This is how they move, but we haven't actually spoken about why do they move. So we are going to talk about why do they move. Okay, so okay, so we're going to be talking about dynamics. Yes. Which one? The okay. ذيك المسألة is, you mean by the train one or the car one? This is our equation. Okay. We have train going at let's forget the train. Let's go directly to the person. We have person going at 28.5 meters per second. We have plane going at 257 meters per second, or kilometers per hour, whatever the unit was. So far, so good. Do we agree on this? This is with respect to ground. This is with respect to ground. Okay. Velocity of plane to person is equal to velocity of plane to ground plus velocity of ground to plane. Sorry, ground to person. I'm going to be using this to person, according to our rule here. Okay, we simply substitute plane ground 257 in this direction. So I'm going to say minus 257 plus yarhamna wa yarhamkum. Velocity of ground person. Person ground is how much? 28.5, right? So ground person x minus 28.5. Number we get is minus 285.5. Just equation. Forget everything else. Okay. All right. So why do objects move? Let's take a ball that is moving from left to right. No worries. Okay. It started with some velocity v1. We finished with some other velocity v2. Now we say the body is accelerating or decelerating, right? Because it went from v1 to v2. The velocity changed. Okay. We call the reason acceleration or deceleration is going on force. Okay. We haven't actually defined what is force yet. We just said it's like magic so far. Okay. Something is accelerating, decelerating, velocity is changing, so we're calling it force. Fine. I know that wasn't velocity of person with the ground. That was velocity of ground with respect to person. That's why we added the minus. Force is a vector. Okay. Now, by the way, if you're going through our book, you will notice that what I'm doing now is slightly here and there, not exactly going through the book one by one, because that's what I will do this a bit later. But first, I want to give you a general idea of how the forces work. Okay. So the direction of a force is important because it is a vector quantity. So we still haven't defined what a force is, but we said that it's a vector and the direction is important. Because it is a vector, we can add them all up just like we did in chapter 2 for vectors. F1, F2, F3. If they are in same directions, if they are in different directions, we can simply add them up using vector notation. If it is at an angle, we can take the components and add those up. So far, so good. متابعين? We still haven't said what a force is. We're just describing what the properties of this magical thing that is called force are. Okay. All right. So net force is the vector sum of all forces on an object. Fine. We come to the principle of superposition of forces, which is what this is. Basically, you have multiple forces, you add them up. Okay. We still don't know what a force is. Now, here's what we say. This is based on observation. This is what Newton said based on observation. Objects will be at rest until a net force acts on it. So things are not going to move unless there is this thing that is called force that causes it to move. الكوز التجريبي مفتوح. Okay. I'll speak about it once we're done with the lecture. Okay. So objects will remain at rest until there is something to cause them to move. That's a really strong woman. Okay. Now we come to definition of forces. Newton's first law of motion. Okay. So Newton's first law of motion is what I call the قانون التمبل. the very boring law. Every object continues in a state of rest or uniform velocity in a straight line as long as no net force acts on it. What did I just say in a very, very long English sentence? Well, here's what it means. If something is not moving, it's not going to move unless there is a force. If something is already moving, it's not going to stop unless you force it to. If something is going in a straight line, it's not going to change direction unless you force it to. If you don't force something to change direction, it will never do so. It will just continue in a straight line. So, long story short, unless you force it to do something, it's not going to do something. Now, Newton said what I just said in a more elegant one sentence. Every object continues in its state of rest or uniform velocity in a straight line as long as no net force acts on it. Okay? If it already has a velocity, it's going to continue at that velocity. I'm too lazy to change anything unless you make me do it. So, which of the following statements can be explained by Newton's first law? When your car suddenly comes to a stop, you move forward. Okay, that's why you need seat belts. And when your car rapidly accelerates, you're pressed backwards against the seat. Okay, now this might not happen if you drive a Corolla, but it might happen if you are driving against the laws. So, excellent. Both A and B. Okay? You stopped your car. When you pressed on the brake, you forced your car to stop, but you didn't do anything to your body. So your body's just going to go, you didn't tell me to stop. I'm just going to continue in a straight line unless there's a seat belt that forces me to go back. When you're accelerating your car, the engine isn't doing really anything to you. It's just moving the car. So your body's like, I'm not going to move. I'm not going to move. I'm just going to go backwards unless you force me. And what happens is once you stick to the back of your seat, the car is moving. So the car forces you to move. So the tendency of an object to maintain its state of rest or uniform motion in a straight line has a name. Okay, what is it called? It's called inertia. Okay, I saw someone who wrote qusur dhati. I have no idea if this is what it's called in Arabic or not. Okay, but in English we call it inertia. Okay. Definition of inertia is resistance to change in the state of motion. Simple. I don't want to change. I'm lazy. Everything in the universe has inertia. Okay. This is the reason why you want to wear seatbelts. Okay. When the car is going 80 or 100 kilometers per hour and you hit something, okay, that force isn't actually on you. It is on the car, which means your body is very happy to keep moving at 80 kilometers per hour. It has no problem with that. You're just going to fly right out the car. Okay, if you have a windshield, you're going to go right through the windshield. Okay, seatbelts, very, very, very important. Okay, let's see if we can understand inertia a bit better. A pipe is bent into the shape shown and is sitting horizontally on a tabletop. So what you're seeing is a pipe going like this, but horizontally on a tabletop. You are looking at it from above. A ball is shot into one end and exits on the other end. Which one of the paths shown will be the ball when it leaves the pipe? Okay. Most of you said 3. Some of you said 2. Now, those of you who said 3 were absolutely correct. Those of you who said 2 did not pay attention when I said that this is horizontal. Now, you would be correct. 2 would be the correct answer if this was a vertical pipe, because you have a force called gravity pulling it downwards. So it's going to go. But on a horizontal table, you don't have any extra forces. Well, gravity is going to pull it down, but you have the table anyway. So what's going to happen is it's going to continue in a straight line until something forces it to stop. Okay. لا ما يروح تحت الأرض. You're horizontal. So if I have this وأجيب لولو وأحطها هنا إنزين, it will just go like this, right? It's not going to go through the paper. So that photo was something that's like this. It's just going to continue going on a straight line. It's not going to drop inside the table. Yes, لو في جاذبية. If the pipe was this way, okay, and the outing was here, the answer would have been 2. It would have gone down because you have a force of gravity going down. Okay. ليش ما واحد? Because remember, you still have a Vx. Remember our question with the in the previous chapter, chapter 4, you have Vx and Vy. So Vy is if you don't have Vx, but since you're coming out of the ball, you already have Vx. So your Vx is not going to suddenly become 0. You're still going to continue. Okay. We spoke about frames of reference a bit ago with the cars and the trains and everything. We actually have 2 types of frames. We have inertial frames and non-inertial frames. How do we define these? Now, there are many definitions, but we're going to use the easiest one. Anywhere where we can use Newton's first laws and our equations of V equals U plus AT, S equals U to UT plus half ET squared, blah, 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 are inertial frames. Anywhere where we cannot use these equations, we need to change them. They're non-inertial frames. We have Earth. It's going round and round and round. Let's just look at the top half. And I am very, very bored. So I'm sitting on top of a satellite outside and just looking at Earth going round and round. And I see a piece of circle just at the North Pole. Now that circle is going to come down, and I'm going to be seeing it going down exactly vertically. Okay. Straight line, perfect straight line. So I get off my satellite, I come all the way down to Earth, I take an airplane, I go to the North Pole, and I look at the exact same disk. But I see something really weird. My disk doesn't go in a straight line. It curves off. I go back outside again, it's still a straight line. I come back inside again, it's curved again. So what is the reason for this? Turns out, over long distances, ground is actually really not is really not an inertial frame. It is non-inertial frame. We would need to make Newton's laws work well on Earth. We would need a fictitious force to explain the deflection. Okay, the Coriolis force is what we call it. Okay, on Earth to fix it over long distances. So we introduce something new, mass, quantity of matter. Large mass, small mass. And we end up at Newton's second law. So we stop the lecture here. It's اختاروا فيل ولا صحار. You can complain about one of them. إما الفيل أو صحار. Okay, that was a joke. We're gonna stop the lecture here today because Newton's second law is another thing, which we will start doing in the next lecture, and then we will continue from there. We took a bit extra time with the we took a bit of extra time with the airplane problem, but that is fine. That is fine as long as we understand. Okay, so with that, we end the lecture. I'm going to stop the recording, and then I need to speak to a couple of people, but first, stop presentation, stop recording.